Assalamualaikum and hello everyone. Welcome back to physics lecture. For this second semester, we are starting our lecture with chapter 1, that is electrostatics. Let us discuss more about electrostatics. So for your information, electrostatics is related to electricity, and electricity is actually made up of electron. Electron is a charge, and charge can be moving and also non-moving, or we call it static. So for this chapter, electrostatics, we only focus on static charge, or charge that is at rest, or it can be moving but with very slow motion. So the case for moving charge is going to be learned from the later in the third chapter. In this chapter, we are having 4 subtopics. They are the first subtopic is Coulomb's law, and the learning outcomes for Coulomb's law are first to state the Coulomb's law, to do the sketching for the electric force diagram, and to apply the Coulomb's law for a system of point charges. Okay class, for your information, electrostatics is also known as static electricity. So kat sini kita nak tengok satu simple demo how to explain static electricity. Okay, on my screen now I have 3 objects. I have a sweater, I have a balloon and a wall. So and these 3 objects are neutral because we can see here the negative and positive charge are balanced. So we can say they are neutral. But if I take this balloon and I rub it to the sweater, okay, you can see that the negative charge from the sweater is transferred to the balloon, right? So the balloon is made up of plastic and the sweater is made up of wool. So because of the material, that's why the negative charge from the sweater is transferred to the balloon. So now these balloons are negatively charged because it is having extra negative charge or extra electrons, and this sweater is positively charged because it has now extra proton. So next, what we do is we move this balloon to the wall, and you can see that when we move this balloon to the wall, the negative charges on the wall are moving to the side. So this is the phenomenon where you can see the negative charge will try to get away from the other side. So this is a phenomenon you can see that the negative charge on the wall are moving away from the negatively charged of the balloon. We can see that from the previous simulation that the unlike charges or different sign of charge will attract, and the like charges or similar sign of charges will repel. This concept is explaining Coulomb's law. This law is named after a physicist called Charles Coulomb, and Coulomb has done an experiment that confirmed the force between 2 static charges. Coulomb's law discussed the force between 2 static charges, and it states that the magnitude of this force between the 2 point charges is actually proportional to the product of charges, and it is inversely proportional to the distance between 2 charges, which means if you bring these 2 charges closer, the force will be bigger. And if we have a bigger magnitude of these 2 charges, you're going to get a bigger force. Mathematically, we can express the Coulomb's law with this equation, where K here is the Coulomb constant, and K can also be expressed as 1 over 4 pi epsilon naught. And the unit for force is Newton. Please bear in your mind that this force is also called as electrostatic force. If you would like to try the simulation by yourself, you can scan this QR code and have a go. As discussed earlier, the force can be attractive and repulsive. It depends on the sign of charges that act between each other. And the motion of these charges is actually telling us the direction of force, which finally will give us electric force diagram. This is how the electric force diagram looks like. It shows us the direction of forces or the motion of the charge. Let us talk about the symbol of the force. So we have one here, F12 and F21. This is charge number 1, this is charge number 2. F12 means the force acted on charge number 2 due to charge number 1. And F12 is the force acted on charge number 1 due to charge number 2. And for your information, both of these forces are having the same magnitude. For the system of charges, we have the first example, positive and positive charge will repel, and the instruction is to draw the direction on the electric force on Q1. So we focus on Q1. We only draw the direction from Q1 because the one that is acting is only at Q1. So positive will repel, meaning this Q1 tends to move to the left. It will try to get away from Q2. So this is the direction of force. So we label it as F12. Force acting on Q1, positive, negative will be attractive. So we label it as F13. Positive, negative is also attractive. So direction is to the left. This is F12. Again, force acting on Q1. Negative, positive, attractive, F14. Negative, positive, attractive, so it's going to be diagonal, F13. Negative, negative, repulsive, so it's going to be to the left. So this is F12. This is the electric force diagram for this case. To help us understand this chapter better, we can always compare this chapter with chapter 8 semester 1. I hope you can still remember. So chapter 8 we have Newton's law of gravitation with equation F equal to gmm over r squared. And for this chapter we have F equal to kq1 q2 over r squared. We can see that there is a similar pattern between these two equations. And what are the difference? We have Newton's law only have attractive force, but Coulomb's law have both attractive and repulsive. Newton's law is due to mass interaction, but for Coulomb's law is due to charge interaction. And Newton's law is a force in a long-range forces, and for Coulomb's law it is a short-range force. Let us proceed with our second subtopic of this chapter, that is electric field. In the subtopic of electric field, we're going to look at the definition of electric field. We're going to use the two equations for electric field, and we do the sketching for electric field strength diagram. This is our Earth, and this is a charge, negative charge. I hope you still remember chapter 8 last semester. Earth has its own gravitational field. So does the charge. Every charge will produce its own electric field. Electric field with symbol E is actually analogous to the gravitational field. The existence of the gravitational field of this Earth is proven when we bring a mass in this region. This mass will experience force. So force per unit mass is equal to gravitational field. For the charge, it is applying the same concept. The electric field is proven exists when we bring a test charge in this region, and this test charge will experience a force. The force per unit charge is equal to electric field. The previous explanation brings us to the proper definition of electric field strength, E. So it is equal to electric force per unit charge. The unit of force is Newton and the unit of charge is Coulomb. Hence, we can have the SI unit for electric field is Newton per Coulomb. The electric field is represented by the electric field lines that is pointing in the direction of electric field vector. Now we have 2 point charges, positive and negative. If we bring a test charge to the region of electric field, this test charge will experience force. So in this case, for positive point charge, the test charge will experience repulsive force, so it will be acting in this direction. If we focus on the negative point charge, the test charge will be attracting to the negative sign of charge. So this positive test charge will be acting in this direction. In order to know the direction of electric field produced by these 2 point charges, positive and negative, that direction of force is taken to be the direction of electric field produced by the point charge. Then we have the outward direction of electric field for positive charge and the inward direction for electric field for the negative charge. In terms of the magnitude of electric field strength, apart from this basic equation, we can have a derived equation that is E is equal to F electrostatic force divided by the test charge. Then we can have E is equal to KQ over R squared. And this is how we draw the direction of electric field at certain point. So in this case, if we have positive point charge, the direction of electric field at this point is going to be to the right. So let's say we have another point here. To draw the direction of electric field, we have to start from, imagine we have outward direction of electric field. So electric field at this point is going to be this direction. For the negative point charge, as the direction of E is inward, so the direction of electric field at this point is going to be to the left. Okay, now we want to look at the direction of electric field at certain point. So we have a positive charge here. So what if I put a point around the region of electric field? So the arrow here is showing us the direction of electric field at that point. So it is always outward. So what if we move the point in the region of electric field? So you can see here the direction is changing. Okay, so if we put the point here, it is upward. If we put a point here, it's going to be downward at that point. And now we place the negative charge. So when we have a negative charge, the direction of electric field always inward. So if we bring closer, the point closer, you can see the strength of the electric field is bigger. So if I put this point here, it's going to be to the right. If I put here, it's going to be to the left. So that is how we determine or we draw the direction of electric field at certain points. Let us do some example for sketching for electric field strength. So the question asks us to draw the direction of electric field at point P. So for number 1, point P is in the middle. We have charge number 1, charge number 2, and both are positive. So with respect to Q1, at point P, direction of electric field is going to be to the right because the direction of electric field is outward. And we label it as E1 because it is from charge number 1. For charge number 2, again the direction is outward because it is positive. So the direction of electric field produced by charge number 2 is to the left at point P. So this is how we sketch the electric field strength for case number 1. For number 2, again we have plus and plus. So it's going to be outward direction of electric field with respect to point P. So this is E1. With respect to point P due to charge number 2, this is how we draw the direction of electric field from charge number 2. Let us proceed with the third subtopic, electric potential. At the end of this session, you should be able to define electric potential, equipotential lines, and use the equation of electric potential. And we want to calculate the potential difference, delta V, deduce the change in potential energy, delta U, and lastly to calculate the potential energy U for a system of point charges. Electric potential is defined as the work done per unit charge to bring a test charge from infinity to a point and electric field produced by a point charge. So we have a point charge and we want to bring a test charge from infinity to a point in electric field. So the work done to bring this charge to this point divided by the magnitude of charge is equal to electric potential. The unit for electric potential is joule per coulomb or volt. Let us explore more about the electric potential. Imagine we have a situation, this is Ali. So imagine Ali wants to push this test charge towards a point charge. So when he pushed the test charge towards the point charge, Ali is actually doing work. So when the test charge is moving to the point charge, this test charge is actually against the repulsive force between these two charges. So when Ali is doing work, his charge is actually against electric potential energy. Electric potential is defined as the electric potential energy at a point in an electric field. So in explanation, sebenarnya kalau kita nak tahu nilai electric potential at this point, as this point is actually in the region of electric field of this point charge, the electric potential at this point is actually telling us the amount of electric potential energy which is equal to the work done by Ali per unit test charge at this point. So that is the meaning of electric potential. The other concept for electric potential is equipotential lines or surfaces. So for this term, we have its definition. It means that in one line of equipotential that is always drawn as dotted line, all points at these lines are having the same electric potential. So let's say we have point A and point B. So potential A is equal to potential B. So when these two potentials are equal, meaning the electric potential difference is 0 because VA is equal to VB. So VA minus VB is equal to 0, which means there will be no work done as the work done is equal to delta V. So since our delta V is equal to 0, so the whole work done will be 0. This equipotential lines is normally drawn as dotted line and it must be perpendicular to the electric field lines. So let's say this is your electric field lines. So we must draw our equipotential lines perpendicular to the electric field lines. So this is our equipotential lines. Based on the given condition, so for an isolated charge, this blue dotted line here is our equipotential lines. And this orange line here is the electric field lines. So you can see here that these two lines are perpendicular to each other at any point. For uniform electric field, this is the lines of electric field. And the dotted blue line here is the equipotential lines that is always perpendicular to each other at any point in the uniform electric field. So this is our equipotential lines. Now we want to deduce the term or the equation for electric potential at a point charge. So the basic equation, please recall, we have looked at V is equal to work done or the electric potential energy per unit charge. So to get the equation for electric potential energy, we have to know the work done. Here is how we deduce the term for the work done by the external force if we want to bring a test charge from point A to point B. So it is undergoing the process of integration from point A to point B. From the term of the work done we have got earlier, then we can have the term for the electric potential energy, that is U is equal to KQQ over R. This is the definition for potential energy. It is equal to the work done to bring a unit positive charge from infinity to a point. So electric potential is equal to electric potential energy per unit charge. So we take the equation that we have got before and divided by the test charge, and finally we have the other term for electric potential, that is KQ over R. So for your information, for electric potential, it must consider the sign of charge. And electric potential is a scalar quantity, means it has no direction. So you will never draw any direction for electric potential. And so does the electric potential energy. Both of these has no direction. So to determine the electric potential for a system of charges, which means a system that has more than one charge, we just do the calculation. There will be no direction drawing or sketching, so we just do the calculation. So for this case, for example, we have Q1, Q2. So Q1 will produce its own potential. Q2 also will produce its own potential. So this is the distance between the point P and the charge R2. This is the distance point P to Q1 R1. So to calculate the electric potential at point P, it is actually electric potential due to charge number 1 at point P plus electric potential due to charge number 2 at point P. So electric potential is KQ1 over R1 plus KQ2 over R2. So this is how we do the calculation. For the second example, if we have 3 charges, meaning you have to add up all the potentials that is possessed by these 3 charges. So potential at point P is going to be potential due to charge number 1 plus potential due to charge number 2 plus potential due to charge number 3. So the thing that you have to be more careful is at the distance. So it's going to be R3, this is going to be R1, and this is going to be your R2. So to get the magnitude of electric potential difference, the concept is the V final, electric potential at final point, minus the electric potential initial. So in this case, we are going to bring our charge from point B to point A. So point A is going to be the electric potential final and point B is going to be electric potential initial. So this is the equation. Or, apart from this equation, you can also use delta V is equal to the work done per unit test charge. And we also have the term for change in electric potential energy, delta U. So delta U is equal to UA minus UB or U final minus U initial. Remember, we have U is equal to QB, that is coming from V is equal to U over Q that we have learned previously. So U is equal to QV, and here we can have QVA minus VB, and it is equal to U is equal to Q delta V, potential difference. And for the electric potential, you have to consider the sign of charge to include in the calculation. For a system of charges, which means a system that has more than one charge, one point charge, the electric potential energy is to add up all the interaction between the charges. So for example, in this case, we have three charges, Q1, Q2, Q3. So in this system, we can see that there are interactions between Q1 and Q3. So it's going to be U13. Interaction between Q2 and Q3. So there is a potential energy U23. And also we have interaction between Q2 and Q1. So for this interaction, there will be an electric potential energy of U12. So for this system, we are having three electric potential energy and we are adding up all the terms and all the potential energies. So this is how we calculate the electric potential energy for a system of charges. And again, the sign of charge must be substituted in the calculation. Now we are at the last subtopic of this chapter, that is charge in a uniform electric field. In this subtopic, I will explain quantitatively with the aid of a diagram the motion of charge in a uniform electric field. And for this uniform electric field, we have a specific equation for the electric field strength. We are going to look at the motion for these four cases. We have motion of stationary charge in between two plates, charge moving perpendicular to the field, charge moving parallel to the field, and charge in dynamic equilibrium. Uniform electric field is special. Why? Because it is only formed in between two plates of opposite sign. So we have plus and negative. So the direction of electric field is always from positive to negative, and the uniform electric field is uniform electric field is represented by a set of electric field lines with a straight, parallel to each other, and equally spaced, meaning the distance between the two lines are the same. So itu maksud equally spaced. The equation for uniform electric field is given by the electric potential divided by the distance between these two plates D. So electric potential here is actually the change in potential, since in this case our change in potential is V minus 0, so it is equal to V. Charge in uniform electric field, we have few cases. So this is the first situation, that is stationary charge. stationary charge is said to be at static equilibrium. So for this condition, the electrostatic force that is acted towards the positive charge, because this is negative, is having the same magnitude with the weight of this charge, but it is acted in different direction or opposite direction. So because of this, it is not moving or stationary. The second case is the charge moving perpendicularly to the field. So we use electron for example. So this electron has mass me and initial velocity u. Okay, what happens here is when this charge is entering the region of uniform electric field, this negative charge will tend to attract to positive charge. Because of the upward electric force, it tends to move to the upward. It will cause the electron to move along the parabolic path. So here is the motion of the electron in the uniform electric field when it is entering perpendicularly to the field. And this is the trace of the path. So this path is called as parabolic path. The parabolic path is always under the influence of acceleration that is coming from the electrostatic force acted on the electron. So that is electrostatic force with equation QE, and QE is equal to ma, the basic equation of force in motion. So here A is equal to Q over m times the electric field strength. So this acceleration is always acted for vertical motion. And again, if this is a parabolic path, you can recall chapter 2 in the previous semester, semester 1, we learned about projectile motion. So in projectile motion, we have a few terms for x and y-axis. We have a few equations. So please recall what you have learned, and you are going to apply this equation for the case of charge moving perpendicularly to the electric field. So ay here for the y-axis is equal to this term of acceleration. Now we look at the third case or the third situation, that is the charge moving parallel to the field. So in this case we have a charge in between the two plates, positive and negative. So when the charge, let's say we have positive charge, so it will tend to attract to negatively plate, so the motion is downward. And if we have negative charge, it will tend to positively plate, so the motion of charge is upward. So when every charge is moving, it will have its own acceleration. Let's say we have the other case. We have upward direction of electric field and we have positive charge. So this positive charge will move upward because it tends to attract to negatively plate. And if we have another example of negative charge, so it will tend to attract to positively plate. So based on the motion previously explained, we have the motion of charge is because of the attraction in the electric field, so it possessed electrostatic force that is equal to QE, and because of the motion, the electrostatic force is equal to ma. So we equate the two terms, and finally we can use the term a for the acceleration, that is equal to q over m times electric field. Q is the magnitude of charge. We can also apply these three kinematic equations to find the velocity, initial velocity, and time, and also displacement for the charge that is moving parallel to the field, as explained just now. Here comes the last case of charge in uniform electric field. So this is the case or the situation for charge in dynamic equilibrium. So for dynamic equilibrium, again we have the electrostatic force that is acted upward and weight acted downward. Both of these forces are having the same magnitude, but it is acting in opposite direction. So the charge will move at constant speed because both will be attracting in opposite direction, and the charge is said to be in dynamic equilibrium. And this is the motion of charge when it is in dynamic equilibrium. So the difference between static equilibrium, as discussed in the first situation, static equilibrium is just about the same with dynamic equilibrium. The static equilibrium, but for static equilibrium, the charge will not move. It is stationary. Okay class, before we stop, last but not least, we do the chapter summary for the whole chapter. So quickly we have, for this chapter, we have 4 basic quantity. We have electrostatic force, we have electric field, we have electric potential and electric potential energy. And this is the, okay, these first 2 quantities are vector quantity. So you have to consider the direction. You have to draw the direction for both quantities. And for calculation, you are not considering the sign of charge. You not include the sign of charge. But for these 2 quantities, it is a scalar quantities. But for these 2 quantities, they are scalar quantities, meaning it has no direction, and you have to include the sign of charge in calculation. And then we have, in the last subtopic, we have the charge in uniform electric field. Okay, uniform electric field. So for this electric field, we have a special equation that is the change in potential divided by the distance between the 2 plates. Okay, so we have a few situations for the charge in between 2 plates of positive and negatively plate. So the direction of electric field is going to be from positive to negative. Okay, so the first case, we have the static equilibrium of the charge. So the charge is in equilibrium with the weight and also the electrostatic force if we have negative charge here. And then we have the second situation is we have the charge that is coming perpendicularly entering the electric field region, uniform electric field. So what happened here is this charge will deflect. It's either to the lower plate or to the upper plate. It depends on the sign of charge. Okay, and the third situation is when the charge is moving parallel to the electric field. It's either upward or downward. It depends on the charge, on the sign of charge. And lastly, we have the charge in dynamic equilibrium. So for dynamic equilibrium, it is again in equilibrium. So you have electrostatic force is balanced with the weight, but this time it is moving with constant velocity in a straight line. So that's all for the chapter summary. Alright, finally we're done chapter 1, electrostatics. Hope it is very helpful for you. Thank you very much.